Section 2.5, Optimization Problems. The idea here is that if we are trying to work in the real world, usually we want to minimize something or we want to maximize something, and because of that we're going to be able to use the derivative to help us find maximums and minimums. And so specifically recall that maximums and minimums are going to occur when the derivative is 0. And so we're going to have to, in some form or fashion, create an equation, take the derivative, figure out where that's 0, then figure out if those zeros are maximums or minimums depending upon our situation, and then answer our questions. So when we're talking about this optimization, we're going to deal with two separate equations. So specifically the first equation is going to be the objective equation. And the objective equation is going to express the quantity to be optimized in terms of some variables. And so there may be one variable, there may be multiple. We might have to do a little bit of work to get it into a single variable. Just be aware that this is where you start. Well, then what's going to happen is you're going to have restrictions. And so we're going to have this thing called constraint equation. And this constraint equation is going to place limits on how variables interact. And so this is usually going to be information that we'll have to extrapolate from what we're told in some word problem. So just be aware there's several parts to this, and we're going to have to walk through some approaches that are some best type of approaches. But recognize that we do have to be a little bit flexible, and we're just trying to use the tools of the derivative to help us find solutions to real-world problems. So, let's remind ourselves real quick, what is the first derivative test? Well, remember that if you can find values, and let's say those values are a, such that the derivative is 0, then those a values are possible extrema. Sometimes we call those critical values. And so the a's are possible extrema. And so we find all our a's that make the first derivative 0, and then we have to confirm whether or not those a's are actually extrema. Now there's two good ways to do it. You could use the second derivative test, but we'll mention that in a moment. But recall that the other way is take the number line, cut it up, and if you put your a values here, let's say that you had 3 zeros, and so I pretend that a1, a2, and a3 are zeros of the first derivative, then what you do is you plug in values in each one of these intervals, and then figure out, does the derivative change from positive to negative across that possible extrema. And so remember that if I have minus plus, well, that means that a1 is extrema, or at least the location of extrema. Whereas let's pretend that on the left side of a2 it's positive when I plug in a value, and on the right of a2 it's positive. No change, so not extrema. And then if I had from plus to minus, this once again is just an example, and so if I change from an increasing function to a decreasing function, then we say that it's extrema. Okay, and so just remember that this is how you can test it using just the first derivative and cutting up a number line. But recall that you can use the second derivative. So remember that if the first derivative for a values gives us 0, then once again a's are possible extrema. This stuff is still applying when we talk about the second derivative test. But specifically, if f double prime of a is greater than 0, then a is a minimum. And remember, that's because if the second derivative is positive at that value a, then specifically we're really saying that we have a concave up function, right? Concave up. And so concave up forces that a value be a minimum. On the other hand, if you take the second derivative, f double prime of our zeros a, and you get that it's less than 0, then a is a maximum. And so specifically, that's that situation where being f double prime of a being less than 0, that specifically creates the concave down situation, and so a would then be a maximum value. And so keep that in mind. You can use the first derivative as standalone, or you can use the first derivative test in conjunction with the second derivative test to verify maximums and minimums. And of course, recall that if you get the second derivative of that value being equal to 0, it's inconclusive, and you're really going to have to return back to cutting up the number line anyway. So just keep these things in mind. Well then, a handful of suggestions I'm going to make for solving optimization problems. Number 1, draw a picture. And I like to say that if we draw a picture, one of two things will happen. Either you'll help keep yourself on track, or if you're like me, you'll at least entertain yourself with your image. And so just draw the picture, get yourself going, because some of these things may not come out clearly unless you draw the picture first. The next thing is decide what's being optimized. That is, decide what is being maximized or minimized. Third, identify restrictions on the situation. Now, when I say identify restrictions on the situation, realize that if we're talking about some length, then usually lengths will not be negative for us, and so you'll automatically have restrictions that may not be stated clearly but are implied, that your values have to be bigger than 0 or equal to 0. And so realize that we need to identify our real-world restrictions on whatever situation is being mentioned. Then assign letters to quantities that could vary. And I'll actually tell you that when I do these things, usually when I start thinking about my picture, all those first 3 items actually, I'm going to go ahead and probably start assigning letters in my pictures and in all these other things as I go, because I realize that certain things may not be locked in, and I'll recognize pretty quickly what's being maximized or minimized based on the letters that I've assigned. Then once again, from your pictures, what's being maximized and minimized, and these restrictions and the letters we've assigned, you're going to form your 2 equations, if you haven't already by this point. And remember that those 2 equations are going to be one for your maximum and minimum quantity, and it may be max or min. Usually we're not doing both. And that maximum or minimum quantity equation is going to be called the objective equation. And the other one is going to be for the restrictions, which is called the constraint equation. Constraint equation. Alright, but then what happens? Then you're going to use the constraint equation to get our objective equation in one variable. And so usually what ends up happening is you'll solve the constraint equation for the variable that you don't want to find, and then replace that, and we'll see this in practice. Then, once you have the variable equation in one variable, use some correlation or combination of the first and second derivative test to find maxes or mins. Then, once you've found maxes or mins, be certain that you answer the question being asked. Because just because we found some value for a maximum or minimum doesn't mean we actually answered the question. And so because we have applications, make sure that you're always paying attention and answer the question that's being asked. So let's just jump into this. So we want to find two numbers whose difference is 100 and the product is a minimum. Alright, so first off, let's always point out what are we going to be answering. Well, the answer to our question is going to be two numbers. We need two numbers whose difference is 100 and product is a minimum. At this point, I just like to kind of write down things that I see. So specifically, the difference is 100. That means I'm going to have two numbers. Well, we don't know what those two numbers are, so let's just give them variables. Why don't we call one of them x and the other one y? So if I have two numbers, x and y, where their difference, that's going to be x minus y, is equal to 100, and product is minimum. So what we want is we want to minimize x times y. So we want x times y to be as small as possible. Okay? I think I've laid out everything I need. We know now some variables that represent the answers to our question. We recognize that we need to minimize a product. We recognize that the difference of those two unknown numbers is going to be equal to 100. Now, at this point, I recognize that if I'm trying to minimize this x times y, this equation here is really my objective equation. And so if this is my objective equation, we know that at some point we'll need to take the derivative of that, but recall that we don't necessarily know how to take derivatives of more than one variable in this class, and that's okay, at least not right now. But we need a second equation to try to figure out how I can write this as in terms of a single equation. Well, if I've got x minus y is equal to 100, this is my constraint equation. So I have a constraint equation, I have an objective equation. We're going to use the constraint equation to write our objective equation in a single variable. And so pick your favorite letter. I'm going to take a wild guess and assume that your favorite in terms of derivatives is x. No requirement. And if this favorite is x, then I want to solve for y. And so since that's the case, how about I take my constraint equation, x minus y is equal to 100, solve it for y, minus x, I get negative y is equal to negative x plus 100. But then I can divide by negative 1, divide by negative 1, and I get that y is equal to x minus 100. And so then I recognize that I can take and replace y in my objective equation. So that's going to be from my objective equation. I can then write it as x times y, but I'm replacing y with this y, x times x minus 100. And now we're in a single variable. And so now specifically I want to minimize this. Alright, so what can we do? Well, of course I can simplify this. This is then going to be x squared minus 100x. And if I want to find possible extrema, remember we just take this function, find the derivative, d dx of x squared minus 100x, that's going to be equal to 2x minus 100. Then possible extrema will occur where the first derivative is equal to 0. And so that's going to be 0 is equal to 2x minus 100. Add 100 to both sides. I then get that this is 100 is equal to 2 times x, divide by 2. Divide by 2, I get that 50 is equal to x. So my possible extrema is at 50. At this point, remember that you have two choices. Either take the second derivative and consider f double prime of this value 50, or cut up the number line. But honestly, I recognize that this is an easy second derivative. So if I take the second derivative, d2 dx2 of x squared minus 100x, well, I'm just taking the derivative of 2x minus 100, which is just going to be 2. Well, my second derivative is positive. Since my second derivative, f double prime of x, is positive, then I guarantee that this is concave up, which is good because that means that this is a minimum. Great, that's exactly what I wanted. I wanted to minimize my product. And so 50 is part of my answer. Well, what in the world do I need to do to answer my actual question? Remember that we had to find two numbers. Well, I found one. X is equal to 50. Well, how can I find the second? Well, recognize that what did we do in the original? X times y is the thing we were trying to minimize, and I had that constraint equation where I found that y was equal to x minus 100. And so now if I want to find that second number y, I just take 50 minus 100, and 50 minus 100 is going to be negative 50. And so I've now discovered that my second number y is really negative 50. Then we're done. We did answer our question. My two numbers are 50 and negative 50. Those two numbers whose difference is 100, and the product is a minimum. Alright, let's try another. You want to build a rectangular fenced area with one side being your house, and then you want to find the max area you can enclose if you only have 100 feet of fencing. Then we also want to know what is the length you would make the side opposite your house. Alright, so really we're going to find two questions. What is the maximum area? And what is the length of the side opposite your house? Now for this one, I claim we definitely want to draw a picture. And so I'm going to draw a poor picture. And I'm going to draw a picture from above. So let's pretend that this is my house. And if that's my house, then let's just do a rectangular fence on the back side. So, rectangular fence, rectangular fence. Now I'm not sure if this is supposed to be the whole length of the house. I have no idea. We'll just leave it like that and see what we have. Alright, but what do we know? Well, we also know that we only have 100 foot of fencing. And so, since we only have 100 foot of fencing, this is actually going to apply to my constraints. So I recognize that that's going to be one of my constraints. It may not be the only one, but it's definitely one of them. Alright, what else can we say? Since we're going to try to find area, they didn't say it, but we're going to need to have an area equation. Well, remember that if I have an area, area is really equal to length times width. Well, since that's the case, let's just assign a length and a width to one of these sides. It doesn't matter, it's kind of arbitrary, but what if I call this length and I call this width? Great. And something to mention that since this is a rectangle, not only is this side length, but this side will also be a length. And this is actually going to apply to my constraints. Now that I have the picture, we should recognize that how much fence can be built. Well, specifically, I know that if I've got length plus width, the maximum that I can get is 100 because that's all the fencing that I currently have to build with. And so this is actually my constraint equation. And this is my objective equation. And so now I have an objective equation, I have a constraint equation. I think I've got everything that I need. At this point, I just need to solve for either L or W in my constraints and replace it. And it doesn't matter which one you solve for, whether you solve for L or you solve for W. Why don't we solve for L? Now, why am I choosing to solve for L? I know that, I remember that one of my questions is the length that you would make the side opposite your house, but in terms of my picture, that's W. And so when I answer the W question, I've answered half of my questions. Alright, so let's see if we can do this. Let's solve for L, so that's going to be 2L plus W is equal to 100. So subtract W, that's then going to be 2L is equal to 100 minus W. Divide by 2, divide by 2. I now have a good equation for L. L is 100 over 2 minus 1/2 W, which is of course 50, and I'm going to write it that way, but I'm just saving space. And so then I can rewrite my area equation. Specifically my area equation, I'm going to replace L with that I just found, which is going to be 50 minus 1/2 W times W. So then I have my area equation, which is going to be 50W minus 1/2 W squared. Well then, what were we trying to maximize? We're trying to maximize the area, which means I now need to take the derivative. So, what's A prime? Well, A prime is then going to be 50 minus 1/2 times 2 times W. 50 minus W. So then, because we're looking for a extrema, I set this equal to 0. 0 is equal to 50 minus W. Subtract 50, subtract 50. I then get that negative 50 is equal to negative W. Divide by negative 1, divide by negative 1. I get that W is equal to 50. Now, if we're talking about units, this is 50 feet. And so, lucky us, we've actually found one of my solutions here. W is equal to 50 feet. Great. Okay, that's wonderful. So I've actually answered this question. Check. I know that the length opposite the house is 50 feet. Well then, they haven't asked for it in this problem, and so they don't want to know length, but I need to find length because I need to know specifically what is the area. And so I want to know what is that maximum area. And so at this point, because I found that W is equal to 50, I just need to find the length. So length is equal to 50 minus 1/2 of W, which is 50 feet. Well, 1/2 of 50 is 25, so 50 minus 25 gives me 25. And so now I know that my length is 25 feet. And so if I know the length and I know the width, and I know that the area that's enclosed is being length times width, or 25 times 50. And so 25 times 50 is 1,250 square feet, or you could write that as feet squared. And now that I read this problem again, since it just said find the max area you can enclose if you only have 100 feet of fencing, well, that's 1,250, but maybe not. My labs maybe didn't want both of these. So specifically, I know that the W, that length of fence opposite the house, is 50 feet. And if somebody asked what's the max area, then we've also found that answer if it was desired. Similar type problem. We want to build a rectangular fenced area with 3 sides made of chain link fence and 1 side made with wood. Chain link costs $10 per foot and wood fencing costs $20 per foot. What is the maximum area if you have a budget of $600? I'm going to start and I'm going to sketch a picture. And I'm going to use 2 colors. I hope that these differentiate okay, but chain link fence is usually a silver or gray color, and so I'm going to stick with 3 sides made of chain link fence in this gray. And then wood is usually a brown color, so just for some contrast I'm going to do dark brown. I guess it really is not distinguishable from black, but this is wood. This is chain link. And so all of this is chain link. Alright, so there's my sketch. This is what I got started. Now at this point, I want to figure out what is the question that I'm being asked. The question is, what is the max area based on a budget? And so maximum area, I have an area equation. This is a rectangular fence, and so again it's going to be length times width. But to keep myself on track, I'm going to recognize that there's a length and there's a width. And so let's say that this side here is my length, and this side here is my width. Now I want to be careful about this because notice that the wood is only one of the four sides, and so there's some stuff that's going to have to come into play here. And we'll deal with that in a moment. But area is equal to length times width. And so I now have an objective equation. The trick here, though, is going to be my constraint equation. And so let's think about constraints. Alright, well specifically we're going to be purchasing chain link and wood in terms of linear feet. And so in terms of linear feet, I need to remind myself that this side is also going to be a length. This side is also going to be a width. Okay, so what's going to happen here? Well, my constraint is a budget of $600. So really that $600 plays a part, but what's it related to? It's related to the cost of the lengths and the widths. And so if I think about this, I know that the wood fence is just one length of W, or one width of W, times the amount of cost per wood, which is going to be $20 per foot. And so width times 20, 20W actually gives me my constraint on the wood, 20W. But then I've got to add in the chain link. Well, then there's going to be 2 lengths of L, so I'm going to say 2L times the cost of the chain link, but chain link's only going to cost $10 per foot, and so that's 10 times 2 times L, plus the last piece of chain link, but that's just going to be another $10 per feet where the feet is measured in my W. And so this is specifically my constraint equation, considering how perimeter works and how cost is going to work linearly. At this point, let's just simplify this equation. Then it's going to be true that $600 is equal to 20W plus 10W, or 30W, plus 10 times 2 is 20 times L. This is my constraint equation. Well, since now I've got an L or a W, I just need to pick one and solve for it. I'm just going to pick L. It doesn't really matter. And so if I solve for L, then I'm going to subtract 30W from both sides. And we get that 600 minus 30W is equal to 20L. Then I'm going to divide everything by 20, divide it all by 20. I then get that this is 600 divided by 20 is 30, minus 30 divided by 20 is just 3/2 W is equal to L. Then I use that constraint equation. I rewrite my objective equation in terms of a single variable. So I'm going to replace the L with this W. So that's going to be A, area, is equal to 30 minus 3/2 W times W. Well, then I can simplify this. That's then going to be 30W minus 3/2 W squared. Then, recalling that I'm trying to maximize my area, I need to take the derivative of the area function. So A prime is just going to be what? Well, that's going to be 30 minus 3/2 times 2 times W to the first, general power rule. So that's then A prime is equal to 30 minus 3W. And then I recall that since I'm trying to find possible extrema, I set that equation equal to 0, solve for W. How about we add 3W, add 3W, 3W is equal to 30, divide by 3, divide by 3, W is then equal to 10. So an important piece of information is that my W's must be equal to 10. Then using my constraint equation, I can plug in that W. That's going to be 30 minus 3/2 W, where W is now 10. And that will give me my length. So 10 times 3/2, 10 divided by 2 is 5. This is 30 minus 15. 30 minus 15 is 15. So I claim that my length is 15. So then I know that length is 15 and length is 15. Now, since this is the situation, I return to what was my question. The question was, what is the maximum area? Well, the maximum area, based on this budget constraint, is then going to be area is equal to length times width. I found the length, it's 15. I found the width, it's 10. 15 times 10 is 150. My units were feet, and so this is now square feet. And so 150 square feet is the maximum area that I could have based on that budget restriction and these costs in play. Alright, so for number 4 here, recognize that this is a similar setup to number 3. But the difference is that they're changing the information we're given. And so they're going to say we need an area of 216 feet, and we don't have a budget. However, this time we want to minimize the cost. And so at this point, recognize that I can look at that picture again. Maybe I'll sketch it one more time for us. Chain link fence on 3 sides, where I have a length, and a width, and a wood fence on this side. That's my wood fence with a width. And at this point, I still have that area formula, where area is equal to length times width, but specifically, the area that I have has been told to me. It's going to be 216 feet squared. And then when I talk about my cost, well, earlier I had a cost of 600, but this time I'm not told the cost. I want to find the cost, and so the cost is then still 20W plus 10 times 2L plus 10 times W, but I'm going to take the simplified form of that, which is just going to be 30W plus 20L. Let's not waste the work we've already done. And then I recognize now that what's really happened is I've changed what's my constraint and what's my objective. So now in this situation, my constraint equation is the area formula. And my cost function is my objective formula. And so those have been swapped on us, but that's perfectly fine. And so now I just need to use my constraint to write this over here in terms of a single value. It doesn't really matter which one we pick. I'm just going to arbitrarily solve for W. And if I solve for W, then that means that W is going to be equal to 216 divided by L. And if I use that, then my cost function can be rewritten as 30 times 216 divided by L plus 20L. I'm going to clean that up a little further so I have less to fight with. 30 times 216, that's going to be 6,480, all divided by L, plus, now I'm going to have to take a derivative, so maybe I want to rewrite it as times L to the negative first, plus 20L. And once again, since we're minimizing cost, I'm going to take the derivative of cost, so this derivative of the cost function that I have here is then going to be equal to negative 6,480 times L to the negative second plus 20 times L. The derivative of that is just 20. And then I'm going to rewrite this because, of course, I need to set this equal to 0. So this is the same thing as negative 6,480 divided by L squared plus 20. I'm going to set that entire thing equal to 0. 0 is then equal to negative 6,480 divided by L squared plus 20. Now at this point, of course, we recognize that L can't be 0. Now that makes sense because if L were 0, then we wouldn't really be building a fence that was a rectangle. We'd build in a straight line of fence, and that's not helpful in any way, shape, or form. So since that's the case, and we know that L is not 0, I can multiply everything by my LCD, where specifically my LCD is L squared. And so L squared times 0 is 0. Then this is going to be negative 6,480 plus 20L squared. Then I need to solve for L squared. So how about I add 6,480? Add 6,480. So 6,480 is equal to 20L squared divided by 20 divided by 20. I get that 324 is equal to L squared. Then take the square root of both sides, technically plus minus. We'll deal with this in a moment. But then I get that L is equal to plus or minus 18. Now I claim that the plus and the minus, one of these doesn't really make sense, because my claim is that if we're trying to get this correct situation, I don't want negative lengths. Tape measures don't come in negative, and so I'm only going to work with the real world value of 18 feet. Okay, great. So now we're almost to our solution. We now know that L is 18 feet. Then I just need to find the width. Well, how did we find the width? We have our constraint equation. That's just going to be that the width is equal to 216 divided by L, or 216 divided by 18, which tells me that the width is going to be 12. Well then, let's remind ourselves, what question are we trying to answer? What question are we trying to answer? We want to know how many total feet of wood and chain link fencing do we buy, and then what ends up being the total cost. So two questions that need to be answered. That is the chain link fence, and let's remember that chain length is going to be 2 L's and a W. So chain link is 2L plus W, and so I'm just referring to my picture there. So that's just going to be 2 times 18 plus the width, 12. I get that I need to purchase 48 feet of chain link, and we also need to figure out the wood, but the wood's just one width length, and so that's just going to be 12 feet of wood. So two of my questions are now answered. And then the last question is, what's that total cost going to be? Well, recall that our total cost function was really going to be C was equal to 30 times W, looking right here, but now we know that W is 12, plus 20 times length, where length is 18, which means that we're going to spend a total of $720 on all that fencing. Alright, an open rectangular box is to be built with a square base. Now the reason it's a square base is because then we know that this right here is actually a square, and if that's a square, the way the side lengths are x and x. Okay, you could also see that if it's a rectangular box, this is that same square. Okay, and the fact that they told us it's a square matters. Then we want to find the values of x and h for which the volume is 32 cubic feet. So I'm going to go ahead and write that. Volume equals 32 cubic feet. And the total surface area is minimized. Alright, so minimize surface area. Now, we do need to recall that the surface area ends up being the sum of the areas of the boxes, and so that's the area of this face plus 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 the area of the bottom that we can't see. And so if we find the areas of all of those things and add them up, we'll have the answer. And so we're going to have to do a little bit of geometry to get the right formulas. Let's find the volume formula. Well, volume is just going to be length times width times height. But because our box base is a square, that's going to be x times h. And so our volume is going to be x squared times h, and that's going to be equal to 32 feet cubed. Hopefully you recognize that because we have a restriction, this is our constraint. And so we now have a constraint formula to work with. Okay? Alright, then we've got to get our surface area, because surface area is going to end up being the thing that we're going to minimize. And so we know that we're going to have to take the derivative of whatever this formula is. Alright, but let's do a little bit of geometry and picture this. Okay, this is a rectangle, a face of a box. Well, what's the area of the rectangle? It's length times width, or length is x, width is h. So, xh for that one. Well, because that base is square, the area here is also going to be xh. The area here is also going to be xh. And the area here is going to be xh. And so since that's the case, I can go ahead and start putting this together. I know that there are four sides. 4 times the areas of each smaller piece, which is 4 times x times h, plus the area of the base. And so what's the area of the base going to be? Well, the base is really going to be, remember, this. That's our base. And so if I want to figure out what's the area of that square, beauty of it is a square, that's just length times width, or x times x. And so x times x is the area of my base. And so the surface area of this box is going to be 4xh plus x times x, or of course that's 4xh plus x squared. Great. Well, we have a constraint formula, we have a surface area formula, but we need our surface area in terms of a single variable. So what are we going to do? We're going to solve our constraint equation for one of these variables. Now, it doesn't matter which one you choose, but part of me thinks that if I were to solve for the h, since it's the only outlier, I'd only have to replace one thing. And so that's exactly what I'm going to do. And so if I solve for h, this then gives me h is equal to 32 divided by x squared, which then if I plug in gives me that 4 times x times 32 divided by x squared plus x squared is my surface area formula. Alright, I'm going to clean it up a little bit. This is then going to be 4 times 32 is 128. X over x squared reduces to 1x in the denominator. I'm going to go ahead and save myself some time because I know that if it's an x in the denominator, I'm going to have to take a derivative, and so I'll probably want it as 128 times x to the negative first, just so I can use the general power rule, plus x squared. Great. So there's our surface area formula. This is the objective equation. Since it's the objective equation, I know it's the thing I'm going to take the derivative of, and so S surface area prime, bad notation, but that function prime is going to be negative 128 times x to the negative second plus 2 times x. Well, then I just want to rewrite this because, of course, since we're minimizing it or maximizing it, to find the extrema, we do have to set that derivative equal to 0. And so that's going to be 0 is equal to negative 128 over x squared plus 2 times x. At this point, I see that I have a rational expression, and if x were 0, this box wouldn't make any sense. It would just be a flat piece of cardboard. And really, I don't know if it would be a flat piece of cardboard, but it would be not a box. And so I can multiply by my least common denominator on both sides, which is x squared. X squared, that's then going to be 0 is equal to negative 128. X squared times 2x is going to be plus 2x cubed. Okay, so then I just need to solve for x cubed. I get that this is 128, add 128 to both sides, is equal to 2x cubed. Divide by 2, divide by 2. I get that x cubed is equal to 64. And then I'm going to take the cube root of both sides, but we don't have to worry about that. The cube root of x cubed is x, and the cube root of 64 is 4. And so my claim is that x is equal to 4. Alright, so if x is equal to 4, x is equal to 4, now I just need to figure out what was the question. So we were told all that information, find the values of x and h where the surface area is minimized. And so the only thing that I need to find is x and h. Well, I also have that via my earlier constraint formula that h is equal to 32 divided by x squared, and so this is then 32 divided by 4 squared, which is going to be 32 divided by 16, or 2. And so now I know that h is equal to 2. And so specifically, those are the solutions that I wanted. X is equal to 4. H is equal to 2. We've found our solutions, and if we really were told to find surface area that we found, we could plug that back into our surface area formula, any of these, to get that area, but we weren't looking for those. So we're done.